So we're supposed to find extreme values of the function. So like we got this function we're going to analyze, this function. So to find those extreme values, what you want to find are something called critical points. Okay? And if you look in the text, critical points are where the derivative equals 0 or where the derivative fails to exist. So for this one, let's take a derivative. So the derivative of an exponential function is itself times a natural log of the base. So natural log e is just 1, right? But then we need the chain rule. The derivative of the innermost function, the derivative of negative x is negative 1. So the derivative is negative e to the negative x. Okay, so that's our derivative, and we said critical points are where the derivative equals 0. So we want to solve this equation. We want to find out what values for x could possibly equal 0 here. And so one trick we have up our sleeve is to resolve negative exponents. We could kick it downstairs into the bottom like this. So the negative 1 stayed up top. Now it's a positive. And if I'm trying to solve for x, I can't solve for it when it's in the denominator. But actually we could just pause here and think. If we plug in any number we want for x, can we ever make the right side equal 0? If x equals 1,000,000,000 or if x equals negative 1,000,000,000, we can get infinitely close, but we never exactly reach 0, right? So for this first question here that I've done, there's no value for x that could ever make this equation be true, and there's also no value that could also make the derivative fail to exist. Remember, you're always looking for those two things. Okay. So there's no critical points. That means the maxes and mins, the extreme values, they have to happen somewhere here in these endpoints. Okay. So again, just that's the big idea, and then I won't keep rehashing this. Critical points are where the potential maxes and mins are. If there are no critical points, maybe I didn't say this, but if there are no critical points like we just found this particular example, then the max and min has to either happen at the beginning of your function, so here at x equals negative 1, or at the end at x equals positive 1. So this one, I analyzed it, found no critical points, so let's find out what happens at the endpoints. If I plug in negative 1 into this function, then negative 1 makes positive 1. If I plug in positive 1 into this function, then I got e to the negative first. So this one is clearly the max, right? And this is the min. So look for those critical points. If they're not there, if there's no critical points, then your maxes and mins have to happen at the start and end of these intervals that you're given. So like in this next one, h of x equals blah, blah, blah. We'll take a derivative to try to find the critical points. So the derivative of natural log is always 1 over the argument, but you need the chain rule. Got to multiply it by the derivative of the innermost function. So the derivative of 2x plus 1 is just 2. So we got 2 over 2x plus 1 for our derivative. Now, we have the derivative. We want critical points. Those are the only places other than the endpoints where you could have maxes or mins. So I set this equal to 0, and then I try to solve. And remember, it's either where the derivative equals 0 or where the derivative fails to exist. Okay. And think about this, if this is our derivative, we can't have divide by 0 problems, right? So at x equals negative 1/2, the derivative is going to fail to exist because 2 times negative 1/2 is negative 1, negative 1 plus 1 is 0, and 2 divided by 0 is something that doesn't exist. So the derivative fails to exist at x equals negative 1/2. Okay, and then if you try to solve this equation, the algebraic step would be to multiply 2x plus 1 to both sides. Okay, and that gets rid of the x in the denominator, but it also makes everything turn to 0 and you get a not true statement. So that means there's no solution. The derivative fails to exist because of a divide by 0 error at x equals negative 1/2. Okay, so that's the value we really want to test. If we were to plug in negative 1/2 back into the original function, because we found out this is our first critical point we found in this class, if you plug negative 1/2 in here, then 2 times negative 1/2 is negative 1, negative 1 plus 1 is 0, and natural log of 0, that also fails to exist. Okay, so we found our critical points. Well, I shouldn't say points. There was one critical point, right? And when we tested it out, the critical point failed to give us our max or min because it wasn't a real value. Okay. So that must mean the maxes and mins happen on the interval, just like on this other one. So far it looks like critical points are useless, right? Because it hasn't helped us at all. But I'm not sure why the book starts with these ones. Usually want students to have success with critical points. But what it guarantees us, though, is that since there's no critical points that actually produce a value like a max or a min, then we know for sure we don't have to worry anymore that the endpoints are at 0 and 3. Those are going to be your potential maxes and mins. And if you plug in 0 into this function, 2 times 0 is 0, 0 plus 1 is 1, so natural log of 1 is 0. And then if you were to plug in 3 into the function, 3 times 2 is 6, 6 plus 1 is 7, so natural log 7. We know that on this interval, this is our max and this is our min, because that's the highest y value, natural log 7, and this is the lowest y value. Okay, maybe we can actually show that critical points are helpful in this next one. So here's our function. We're asked to analyze it on this interval. So if I take a derivative, the derivative of cosine is negative sine, and then we want to multiply it by the derivative of the innermost function, but the derivative of x minus pi over 4, that's just 1, right? So this is our derivative. We want to set our derivative equal to 0 and solve. Okay, and so if we haven't done a lot of trig equations where we try to solve for a trigonometric equation, the first thing to do would be to simplify the trig expression as much as we can. So there's a negative 1 times sine, so we can divide both sides by negative 1. And then for sine to equal 0, remember that sine represents the y coordinates on the unit circle, right? So this would be where sine equals 0, because on the unit circle this is 1 comma 0. And this would be negative 1 comma 0. So there's two places actually. At x equals 0, which is within our interval, and at x equals pi, which is not between these two numbers. So there's two places that would make this equal 0. At x equals 0, or at x equals, sorry, I shouldn't say x, at theta equals 0 and theta equals pi. There's two places where the y coordinate equals 0 on the unit circle. And if you're dealing with cosine, if you're doing a similar problem, you're dealing with cosine, just remember cosine are the x coordinates on the unit circle. So this would be where cosine could potentially equal 0 at pi over 2. Okay, so what would it take to make this inside equal 0, which is we said theta needs to equal 0 to get sine of 0. So we need x to be a number such that sine is of 0. So we just need to figure out what it would take to make this parentheses equal 0, in other words. So pi over 4 is what we need, right? Because pi over 4 minus pi over 4 makes 0. So at x equals pi over 4, we just found a critical point. Okay? You can plug in pi over 4 into this equation. You get 0, and sine of 0 equals 0. That makes our derivative equal 0. So this is our critical point. We just don't know whether it's a max or min. With all critical points, you've got to test them to see whether they're maximum or minimum. Maxima or minima, I should say. So if I test that out, here, I'll give myself a little more room. I need to plug this back into the original expression, f of x. So I'm going to plug in pi over 4 equals cosine x minus pi over 4. X is pi over 4. We're plugging it back in to see what type of value we get. So when you simplify, that's cosine of 0. And cosine is the x coordinates, right? So if we're remember what's inside of a parentheses of a trig function is always an angle measurement, right? So this is saying an angle of 0, which means we don't do any rotation. We're talking about this right here. So that's this point 1 comma 0 in the unit circle. So cosine is the x coordinates. So this would be cosine. It's 1. Okay. I think that's it. So, we plugged in pi over 4. We get out 1 for a y value. And so we need to figure out whether that's a max or a min. So we can find that out by testing out another value. Let's try negative pi over 2. If I plug in our left endpoint, and if I find out that this is smaller than 1, then we know we've hit our maximum. If this is bigger than 1, then we know we've hit a minimum. So we're plugging this back into the original function, the cosine I'm plugging in negative pi over 2 to see what type of y value I get out. So minus pi over 4. So if I simplify that, that's cosine. So it's negative 2 pi over 4 minus pi over 4. So that's negative 3 pi over 4. And if you need to analyze negative 3 pi over 4, sometimes it's easier to think about that in terms of degrees, or you could just use a calculator, I guess. But negative 3 pi over 4, you take the fraction you're working with, cut out the pi, and multiply it to 180. Remember, that's the quick way of converting to degrees. So it's negative 135 degrees. So it lands us right here. So that means we have a 45-degree angle here. Okay. So we're talking about a triangle with a 45-degree angle. So that's that square root of 2 over 2 triangle that we talked about at the beginning of class. But these are negative. Both these are negative, right? Because this is the negative side of the x-axis, the negative side of the y-axis. So cosine is the, and the hypotenuse is always 1. So cosine is always, oops, there we go. Cosine is always the adjacent divided by the hypotenuse, right? So it's the adjacent divided by the hypotenuse. So this is negative square root of 2 over 2. Okay, so we plugged in the left end point. We got negative square root of 2 over 2. So it looks like the critical point we found was a maximum. Positive 1 is higher than negative square root of 2 over 2. Okay? And then you could plug in pi over 2 to be sure. If you do that, you're going to get negative. If you plug in cosine, so if you plug in pi over 2 in here, then that's 2 pi over 4 minus pi over, so that's going to be cosine pi over 4, which is going to give you positive square root of 2 over 2. So I plug this in for you real quick. I got positive square root of 2 over 2, which is a little bit less than 1, right? So we were right. The critical point didn't lie to us. It told us an absolute max on this interval. And you could double check all these by graphing, right? Here, let's go to desmos.com/calculator, cosine x minus pi over 4. Cosine x minus pi over 4. The interval we were talking about was just between negative pi over 2 and pi over 2. Okay? So here's x equals negative pi over 2. And x equals pi over 2. Okay? So we set at x equals 1, this new line that's showing up, that's our maximum. Oh wait, no, what did we say? Sorry, no, at x equals pi over 4 we said our maximum occurs. And we said the maximum was 1. I got those backwards. So we set at pi over 4. The critical point said that was going to be our maximum. Look, it did it. We didn't look at this graph before. We took a derivative. We set it equal to 0. And when we did that, we got a maximum of at pi over 4 comma 1. Right? So the critical point lets you find out what that maximum is without having to click around with a graphing calculator. Obviously, we have the technology, but there's sometimes where we need to be the ones creating the technology and telling the computer how to find those maxes and mins. Okay, can't feed everything through Desmos all the time. And later on in math, when you're proving something, you're trying to prove that this is a maximum. Well, take a derivative and set it equal to 0. All those places where that equals 0, or all the places where the derivative fails to exist, those are all the places where you could potentially have a max and min, other than the endpoints. Okay, so that one was trig, so it took a lot longer. But you know, for this stuff where I was doing it without a calculator, go ahead and use a calculator if you're really struggling at this point in the course. Okay, because there's battles that we're gonna have to pick. So when I did this part right here, that part might have lost some students. We tried to catch up on that at the beginning of the course. Just go ahead and use a calculator, cosine negative 3 pi over 4 at this point, and you should get this as a decimal approximation. Okay, last one here. This one is going to be a lot easier because there's no trig. We're supposed to find all the extreme values using analytical methods. So we want to take a derivative. So I'm using the power rule. The 3/5 came down and multiplied, but now 3/5 subtracted by 1, that's negative 2/5. Okay? And then I want to set my derivative equal to 0. And now look, that's x to the negative 2/5. That's sometimes hard to analyze when it's a negative exponent, so we'll put this in the denominator. And so what would it take to make this right side equal 0? Maybe we have trouble with this fractional exponent. We can rearrange it a little bit so we don't have a fractional exponent. You can have 3x over 5x to the 3/5. No, sorry, that's we want x in the denominator. 1 second. We want 3/5 up here. And I'll show you why. Because if you have x to the 3/5 divided by x to the first, the powers subtract, right, when you're dividing them. So 3/5 minus 1 makes negative 2/5, which is right where we started from. So this derivative is going to fail to exist. I guess that in this case that didn't help us pull out any extra information, but that's something I always do. I rearrange so that I can hopefully avoid missing anything. That didn't help us find anything new though. X equals 0 is a place that would cause the derivative to fail to exist, right? Because we have a divide by 0 problem. And so that means x equals 0 is a critical point. Any place where the derivative equals 0 or where the derivative fails to exist is a critical point. So we want to analyze x equals 0 to see if that's possibly a max or a min. So we can go back in here and we can plug in x equals 0 into the original function. So if you need help with that in a calculator, you're trying to do 0 to the 3/5 power. So 3/5 is 0.6. That's 0. Okay. So we got a real value when we plugged in our critical point at f of 0. If we plug 0 into the original function, we get out 0. Now that's a max or a min. That's a potential max or min. We just got to test it out to see whether it really is a max or min. So that's where it's a good idea to try out the endpoints, see what y values we get for those. If I plug in negative 2, I stopped the video because I was using a calculator incorrectly, so let me back this up. This part's fine, but then when I plugged in this negative 2, my Windows calculator didn't do it the way I thought it would. So here's a website I often use. It's desmos.com/scientific. Okay, and I needed to do negative 2 to the 3/5 power, right? So that's 0.6. So I got negative 1.52. So at f of negative 2, I got negative 1.52. Okay, and then the other endpoint, if I plug in f of 3, 3 to the 0.6 power, I got 1.93 roughly. Okay, so remember, when we say critical points are potential maxes or mins, that's why we say we got to test them. In this case, 0 wasn't a minimum or a maximum, right? The left endpoint had something smaller than it. The right endpoint had something bigger. So the maximum value occurs at x equals 3. The minimum value on this interval occurs at x equals negative 2. So the critical point did not turn out to be the absolute max or absolute min. It's just all the potential places where the max or min could occur. You might be thinking, why do we do critical points if it doesn't guarantee us it's the max and the min anyway? It's because out of the infinite amount of points in your function, critical points guarantee you that these are the only other potential starting or ending, the only other potential maxes or mins, right? You don't have to just go searching and guessing and checking and trying out a bunch of different numbers. You know that if it's a continuous function, the max and the min has to happen at the starting point of your interval, like at negative 2, or it has to happen at the ending point, or the only other places are critical points.